Hello! I'm Professor Von Schmohawk, and welcome to YU. So far, we have introduced quadratic functions and have seen that the graph of a quadratic function in a single variable is a parabola. If we set a quadratic function equal to 0, we produce a quadratic equation. Although quadratic functions and quadratic equations look similar, there are some important differences. For example, let's take the quadratic function x squared minus 4. Like all quadratic functions, the graph of this function is a parabola. Now, if we set this function equal to 0, we produce a quadratic equation. This equation has two solutions, x equals 2 and x equals negative 2. So although the graph of the function x squared minus 4 is a parabola, the solutions to the quadratic equation are the 2 points where the parabola intersects the x-axis, also known as its x-intercepts. These points are called the zeros of the function. In general, the zeros of a function are the input values that cause the function's output to have a value of 0. So for a function of x, the values of x which cause the function to produce a value of 0 are the zeros of the function. These zeros are sometimes called the roots of the function. Finding the zeros of a linear function is easy, since unless the function's graph is a horizontal line, it will always have a single x-intercept and thus a single zero. To find the zero of a linear function, we determine its x-intercept by setting the function equal to 0 and then solving the equation for x. On the other hand, a quadratic function of a real variable may have two x-intercepts, one x-intercept, or no x-intercepts. But solving a quadratic equation can be much more complicated than solving a linear equation. The problem of finding the solution to simple quadratic equations was encountered at least 4,000 years ago by both the Babylonians and the Egyptians. Since ancient peoples did not have the benefit of algebraic equations, they described their procedures using words and pictures. In those ancient times, problems involving squares of quantities typically came up when calculating the areas and dimensions of structures or plots of land. For example, in Babylonia, a standard measurement of length was the ninden. And for a standard unit of area, 1 square ninden was defined as 1 saw, equal to about 36 square meters. A problem involving quadratics that the Babylonians might have to solve would be to find the length of the sides of a square storage chamber, which must have an area of 16 saw. In modern algebraic terms, we could represent this problem by the equation x squared equals 16, where x represents the unknown length of the chamber's side. This is equivalent to solving the quadratic equation x squared minus 16 equals 0. In this case, since length must always be a positive value, the value of x can be found by taking the square root of 16. Which the Babylonians and Egyptians did by referring to tables of square roots written on clay tablets or papyrus scrolls. A more difficult problem might be to find the length of the sides of a square storage chamber with an additional 3 Ninden long extension, where the total storage area must be 28 sa. This problem could be represented by the equation x squared plus 3x equals 28. Or subtracting 28 from both sides, the equation could be written as x squared plus 3x minus 28 equals 0. Solving this quadratic equation is more complicated than just taking a square root, so procedures had to be developed by the Babylonians to solve more general types of quadratic problems like this one. In more recent times, many types of problems have been discovered which can be represented by quadratic equations. For instance, the trajectory of a free-falling object can be described by a quadratic equation. As an example, if a cannonball is fired from a cannon 12 meters above the ground, and the cannonball has an initial vertical velocity of 80 meters per second, then according to the laws of Newtonian mechanics, the height of the cannonball above the ground would be given by the function -5t squared plus 80t plus 12, where the constants in this quadratic expression are determined by the physical parameters of the example, and t is the time elapsed after the cannon is fired. If we wish to find the time it takes for the cannonball to hit the ground, we set this expression for the vertical height equal to 0. And solve the resulting quadratic equation for t. Solving this equation requires a mathematical technique more powerful than anything that the Babylonians or Egyptians had in their mathematical bag of tricks. In the next several lectures, we will explore techniques for solving quadratic equations and see how these techniques evolve through the centuries, eventually allowing us to find the solutions to any quadratic equation.